welcome. This is the last lecture for the module 1 for this course. This lecture is about the curvilinear coordinate system. So, specially we will discuss about the orthogonal curvilinear coordinate system. Now, some of the first of all, why do we need to have different coordinate system except Cartesian coordinate system? Because we are very familiar with the Cartesian coordinate system and we learn all quantities in Cartesian coordinate system. But due to the symmetry or more specifically the rotational symmetry of the geometry, we sometimes need to use different coordinate system, and using these different coordinate system we may get some advantage. Specifically, we will see it when we are dealing with the specific geometry for a specific problem, for instance axisymmetric problems in elasticity or some cylindrical problems in elasticity, where we will specifically use different coordinate system other than the curvilinear coordinate system. Now, we will not talk about the general curvilinear coordinate system here, rather we will talk about the orthogonal curvilinear coordinate system. Now, this term, the term orthogonal means all we know that if there is a basis vector I, j, k in the Cartesian coordinate system, then I can simply write it as I dot I equals to 1 and I dot j equals to 0 and other for instance j dot k equals to 0. So, these are the orthogonal coordinate system. Now, not only these coordinate system, the Cartesian coordinate system we follow is orthogonal, rather we follow it we also say these coordinate systems are orthonormal. What do we mean by the orthonormal? Orthonormal means these unit vector, for instance in this figure it is shown as E1, E2 and E3. These vectors, these unit vectors is essentially of magnitude 1. These vectors have magnitude 1, and similar to the definition of the orthogonal system, E1 or EI dot Ej equals to 1 if I equals to j and equals to 0 if I not equals to j. Now, this coordinate system we are very familiar with, and this is known as the Cartesian coordinate system. Now, suppose I want to define another coordinate system which probably you have seen in some of the courses or some of the lectures earlier. One of them is cylindrical coordinate system. So, where we defined the coordinate system as r theta z coordinate. So, instead of x1, x2, x3 we define as r theta z coordinate. Similar to cylindrical coordinate system, we also have used sometimes the spherical coordinate system. For instance, the spherical coordinate system where you define as r theta phi or r theta xi, whatever it is, and these coordinate systems are related with the Cartesian coordinate system like this. For instance, r is x1 square, x2 square, x3 square, and phi is cos inverse or arctan of x3 by root over r, and then theta is tan inverse x2 by x1. So, this type of coordinate system we have probably seen earlier. Now, our main objective for this lecture is to define our quantities which we have learned in tensor quantities or vector quantities, we have learned in Cartesian coordinate system, what it will take in the curvilinear coordinate system, or specifically cylindrical coordinate system or spherical coordinate system. In this course, we will be mainly using cylindrical and spherical coordinate systems. So, there are other coordinate systems which do exist, but we will not consider these coordinate system, and we will mostly consider only cylindrical and spherical coordinate system. Now, let us define in general what is the relation between the Cartesian and any orthogonal curvilinear system, and then we will go for a specific case for a cylindrical coordinate system. So, let us consider that x be a position vector with a Cartesian coordinates x, y, z and its curvilinear coordinates xi1, xi2, xi3. So, now if this is the case, then any differential element I can define it dx as, which is dx by d xi into d xi. So, partial of the dx. So, this has to be the summation of I equals to 1 to 3, and if you now expand it. So, if you expand it, I just multiply a term h I and divide by a term h I here, and then I defined h I as the del x by del xi I. So, which is known as the scale factor of a curvilinear coordinate system. Now, if I now define my curvilinear basis, for instance E I, which is 1 by h I del x by del xi. Now, here it has to be remembered that it is no sum on I. So, now also it is clear, since we are defining this vector dividing this vector with h I. So, these E I's are of unit magnitude, because h I is the magnitude of this vector. So, these vectors are unit magnitude. So, my final dx is essentially h I d xi I into the vector unit vector. So, these vectors I termed as orthogonal curvilinear system. Now, you see there are one important thing here. In case of a Cartesian coordinate system, the coordinate axis, all coordinate axis is straight line, right. So, the direction in this coordinate system, or specifically the Cartesian coordinate system, does not change as you move from point to point. But on contrary, this Cartesian coordinate system, these vectors may change the direction. This is one of the important distinction between the Cartesian coordinate system and the curvilinear coordinate system. Now, so this is the general formula for which we can derive for any coordinate system, whether it is a Cartesian coordinate system or it is a cylindrical coordinate system or spherical coordinate system. Now, for instance, if I want to consider a length element or the length of a vector, I can just simply take the dot product of a differential this dx dot dx, and which by this formula we can just calculate the what is the length of a vector, or specifically the length of a length square. So, which is essentially h1 d xi I square. So, h I square and d xi I square, which is a simple dot product. Now, here it is used that these EIs, or since these EIs are orthogonal to each other, so I use this relation EI dot Uj is 1 when I equals to j and equals to 0, sorry, when I equals to j and equals to 0 when I not equals to j. So, this relation I have used in deriving this in quantity. So, this become the length become a scalar coordinate. Similarly, the surface of a body. So, that surface of a body we can define as a cross product between the coordinates or the basis vector along xi1 and xi2. So, which is essentially del x by del xi1 and del x by del cross product of del x del xi2 and then its magnitude. So, if you write this specifically in orthogonal coordinate system. So, you will simply just h1 and h2 it will come out from, and these vectors will be e1 and e1 cross e2. Now, e1 cross e2 is essentially your e3. So, this is the relation we know from our orthogonality relation. So, e1 cross e2 is essentially e3 and mod of e3 is, or the magnitude of e3 is essentially 1. So, this quantity becomes the surface area. So, now you see carefully that h1 and h2 is getting multiplied with the usual d xi and d xi2. So, this is actually the difference, the scale factor, which is essentially the term you need to consider when you talk about the general curvilinear coordinate system. Similarly, the volume of an element, which we know from our knowledge of Cartesian coordinate system, is it is the scalar triple product, or dx d xi dx d xi2 dx d xi3. So, this is the scalar triple product formula, and so if I write it in this form, then this scalar triple product will similarly h1 h2 h3, and this scalar triple product will becomes 1 because it is an orthogonal with a or specifically orthonormal. So, its determinant will be 1. So, now this quantity will be just this thing. So, this is altogether the general curvilinear coordinate system. Now, if you remember that we talk about the transformation of the coordinate system. So, when we transform from one coordinate to another coordinate, we really use the transformation matrix or the rotation matrix. Similarly, in this case, when we transform from a Cartesian coordinate system to a cylindrical coordinate system, we use the rotation matrix. Now, suppose there is a position vector in Cartesian coordinate system. Here I am denoting the basis vector for Cartesian coordinate system as I, j, k, and for the curvilinear coordinate system e1, e2, e3. Now, as we know from our transformation rule, so a vector is transformed with a matrix. So, now e1 can be simply transformed q transpose I, e2 can be represented at q transpose j, and so on. So, now for example, if you see the cylindrical coordinate system, which is x1, x2, x3 is related as r cos theta, r sin theta and z, then the basis vector again we compute it from our previous formula, which is essentially del x by del r. So, cos theta I, and then sin theta del x2 by del r, which is sin theta j, and del x3 by del z, which is del x3 by del r, which is 0 here. So, similarly E theta we can compute, and E z we can compute as k only, and but it is notable that h1, h2 and h3 is like this. So, h1 equals to 1, h2 equals to r, and h3 equals to 1. Now, if you use this formula, so what will be the Q matrix for the orthogonal cylindrical system. So, now this Q matrix turns out to be this. Now, if I want to have a two Cartesian coordinate system, this Q matrix is essentially identity matrix. Now, since this is a cylindrical coordinate system, so we will have this Q1. These elements are not identity, rather it is cos theta, sin theta, and 1 for the z coordinate. Now, our main objective here is to define the quantities which are in the Cartesian coordinate system. We learn, for instance, gradient, divergence, and the curl, all those quantities, how we can derive it through the Cartesian. Derive it in the Cartesian coordinate system. Now, we want to see the form how it takes in the general cylindrical coordinate system. For instance, let us talk about the gradient of a scalar. So, scalar we know in the Cartesian coordinate system, which is del del xi, del del yj and del del zk with scalar function phi. So, del phi is essentially del phi del xi, del phi del yj and del phi del zk. Now, in a orthogonal curvilinear coordinate system, these quantities will be like this, because we will have these h1, h2, h3 will be non-zero. Now, if we now specify it for the cylindrical coordinate system, it is essentially, we know h1 equals to 1 for cylindrical coordinate system, h2 equals to r and h3 equals to 1. So, it will be del phi del r er 1 by r, del phi del theta e theta and del phi del z e z. Now, let us consider for a divergence of a vector. Now, divergence of a vector in a Cartesian coordinate system, what we do? We take the del operator or the nabla operator, del del x I, del del x y, del del y z, y j and del del z with the dot product of a component of a vector vx, v theta, vx, vy and vz, and we take the dot product like this. Now, if we do so, divergence of a vector field is essentially a scalar. So, this is how we compute it. Now, in case of a cylindrical system, if we do the same thing, so it turns out to be this, because since this is a orthogonal and orthonormal basis, so e theta er dot er and e theta and dot e theta will be 1, and if r not equals to theta, then it will be 0. So, this is most of us do mistake by doing this, because this is not true actually. Why it is not true, we will see in a next slide. So, most of us does this mistake, just it represents in a Cartesian system, we represent it the way we represent it in a Cartesian system. In a cylindrical system, we also represented it in the same way, but it is not true. Let us see why it is not true and what is the difference. Now, let us expand del dot v. So, del dot v is this, and which is, I have explained why this is not true. We will see it. Now, if you carefully do this dot product, so which is essentially del del r of Vr Er. So, this vector comes here, this vector V is comes each of the term here, and it is dot product with this. So, similarly, del del theta of vector V with dot product of 1 by r e theta. Similarly, del del z of vector V with dot product of E z. Now, if we expand it, so in each term we expand it very in a religious manner. If we expand this each term, so del del r Vr Er dot Er. So, this is the first term we have. So, the second term del del r of del del r of Er Vr. So, this is a product of two functions. So, essentially Vr could be a function of r and Er could be a function of r. So, in case of a Cartesian coordinate system, we do not see this difference, because in a Cartesian coordinate system I, j, k's are constant, essentially are not the function of the coordinate variables. But here Er could be a function of r. So, that is why the derivative with respect to r may not vanish. So, this quantity comes here. So, each term essentially is differentiated two times, because it is a product of two function, one scalar function, one vector function. Now, similarly v theta e theta, we can expand it dv theta dr e theta dot er and v theta d e theta dr dot er, and vz dr ez dot er and d ez dr dot er. Similarly, the second term we expand 1 by r del v r d theta, er dot e theta, and so on. So now similarly the third term we expand in this manner. Now we see what is the consequence. So since this is a orthogonal or orthonormal curvilinear coordinate system or the cylindrical coordinate system, so er dot er will be 1. So del er by del r. So the first quantity del er by del r, if you remember, our er is essentially cos theta I plus sin theta j. So it is not a function of r. So that is why this quantity will be 0. So this quantity goes off. Now similarly E theta er will be 0 because it is a orthogonal system. So this quantity will also goes to 0. Similarly del E theta del r. So E theta is also not a function of r because we know E theta is essentially minus sin theta I plus cos theta j. Now if we see E theta is not a function of r, so this quantity will be 0. So this cancels. So now E z dot er. So E z dot er is will be 0 because it is a orthogonal system. So this cancels. So now del E z by del r. So E z we know for our cylindrical system which is only k. So this quantity will again be 0 because it is not a function of k. Now the next term er E theta, again it will be 0 because this term is, since it is an orthogonal system, so this term will be 0. Now del er del theta. Now if you remember carefully that er is a function of theta, so its derivative need not be 0. So we will investigate later. So similarly del v theta d theta, so E theta dot E theta, so which will be 1, and del E theta again this will be not 0 because E theta is a function of theta, and E z E theta this will be 0 because it is an orthogonal system. Now similarly del E z d theta which is not a function of theta, so then this term will be 0. Now again the last part, the er dot Ez will be, this will be 0, and del er by dz, since er is not a function of z, so this quantity will be 0, E theta Ez will be 0. So and d E theta dh will be again 0 because E theta is not a function of z, but Ez dot Ez this will be 1. Now del Ez by Ez again it is not a function of z, so this will be 0. Now so finally what are the terms we will have? We will have del Vr del r, Er dot Er will be 1, and the next term will have del Vr 1 by r, del Er by del theta dot E theta, and 1 by r del V theta d theta, right, because E theta will be E theta dot E theta will be 0, and similarly 1 by r V theta del E theta d theta dot E theta, and this will be 1. So this will be your the last term. Now let us see what happens to the others. So now so our most non-zero terms are, all non-zero terms are these. Now since we know the basis Er E theta Ez, so dr d theta is essentially minus sin theta plus cos theta j. So which is again it is an E theta, and d E theta by d theta it is minus Er. So in this way actually we can substitute it. So we if we substitute it in place of dr, d of Er d theta, so which is again E theta, so E theta dot E theta, and then this quantity 1 by r del v theta d theta remains unchanged, and then 1 by r v theta del e theta by d theta, which is minus e r. So, I substitute minus e r here. So, it becomes minus e r dot e theta and del v z d z. So, now this quantity is again remains same, and since this is 1, e theta is 1. So, this will becomes V r by r and 1 by r del v theta d theta, and then the last quantity, this E r dot E theta is essentially 0, because it is an orthogonal system. So, when r not equals to theta, it will be 0. So, this quantity again vanish. So, this quantity goes to 0 and del v z d z. So, finally, our non-zero terms will be this plus this plus this plus this. So, this is the gradient divergence of a vector field. So, now you see there is a in a Cartesian coordinate system, the del dot v is, we represent del v x del x plus del v y del y plus del v z del z. Now, if we explain it clearly, why this change is here, because derivative of the Cartesian derivative of the curvilinear coordinate system are not necessarily 0. So, this is proved by this fact. So, now the curvilinear case, the expression for the gradient or the divergence will be different. Now, similar with this logic, we can extend it for the gradient of a or the curl of a vector field. So, that is cross product. So, similar to this, we can just expand it with the cross product. So, individually you have to take cross product with r. So, del r of that vector v. So, this is vector v. So, cross product with r, and then del r vector v cross product of 1 by r e theta. So, this is again vector v. So, this is again vector v. So, in the cross product of E z. So, now if you expand and use those quantities, the derivatives with respect to the coordinate variables. So, we come up with this formula. So, which is pretty different from the Cartesian system. So, this we can achieve. Now, for instance, the gradient of a vector field. So, we know that the gradient of a vector field is del v I del x j e I tensor product E j. Now, if this quantity we have to evaluate in a Cartesian in a cylindrical system, similar to the previous process, the vector field is essentially the v, and this v has to be taken tensor product with the each of this basis vector in the cylindrical system, which I have done here. And so, if you do some manipulation, you come up with this formula. This is a long formula. So, you can just try it and use the derivatives of the basis vector with respect to the coordinate variables to come up with this formula. Now, if suppose we can also find out the different formulas which is related to the orthogonal coordinate system or cylindrical coordinate system. For instance, if I want to find out the Laplacian, for instance, if I want to find out the Laplacian, or which is essentially the del square phi. So, we know the del square phi is like this. So, del square phi is essentially del dot del phi. So, this we know. Now, del dot this del phi we know from our previous expression how to do it for the scalar quantity, scalar function, which is del r of phi E r plus 1 by r del phi of d theta into E theta plus del z of phi and Ez. So, now you see this is again a vector. So, this quantity is again a vector. So, I can write it as del dot vector v, or the let us assume now this vector is v. Now, so see, if we use the divergence formula here, we can compute the Laplacian. So, so now my del square phi will be using this formula. So, del Vr by del r. So, the first Vr will be the del phi del r and then Er. So, the first quantity will be del square phi by del r square, right. And similar to this, that Vr by r. So, Vr we know, so which is 1 by r del phi by del r, and then 1 by r del phi by del theta, or del v theta by del theta. So, 1 by r del square phi by del theta square, 1 by r square del square phi by del square del theta 2, and then the last term is essentially del square phi by del z. So, this way we can del z 2. So, this way we can compute the Laplacian in a curvilinear coordinate system. Now, for instance, if we want to have suppose if we want to have a cylindrical coordinate system where we essentially know the variable, for instance, if we want to have this x is r sin psi cos theta, y is r sin psi sin theta, and z is r cos psi. So, if this is my relation for the spherical coordinate system, so we can easily compute the basis vector. So, basis vector E r is essentially your sin psi cos theta sin psi sin theta and cos psi. So, this is my ER, and then simply E theta if I write E psi if I write, so which is r cos psi cos theta cos psi sin theta and minus sin psi. Similarly, E theta if I write, which is minus sin theta cos theta and 0. So, once we know this, we can compute the other quantities. For instance, the H1 is H1 is 1, H2 is R, and H3 is essentially R sin psi. So, now if we know this, we can compute the gradient of a scalar function, which is or the grad phi, which is again del phi by del r E r plus 1 by r del phi by del psi into E psi plus del 1 by r sin psi del phi by del theta into E theta. So, you see the formula remains same. So, if you remember for the cylindrical system, what was the case for the cylindrical system? The cylindrical system, the case was del phi was del phi by del r E r plus 1 by r del phi by del theta E theta plus del phi by del z E z. Now, where x is related with this r cos theta, y is r sin theta, and z is only k, or z is z only. So, if you relate this with the spherical system, you see only the H1 H2, if you remember the H1 H2 H3 for the cylindrical system, which is 1, H2 is r, H3 is 1. So, you see the only H1 H2 H3 here changes. So, which is essentially your 1 by r and 1 by r sin xi. So, this way we can compute any quantity in a cylindrical or spherical system. So, this is just a exercise keeping in mind that with H1 H2 H3 and the basis vector E1 or the ER E xi E theta. So, all the quantities which we can calculate in the cylindrical system or Cartesian system can be converted to the spherical system as well. So, now so this actually helps us in doing some of the problems. So, now in the next module we will be discussing about the concept of stress and strain, and this module, actually with this lecture, this module we finish the introduction to the tensor. Thank you.